Hello, calculus students and seekers of truth. Today we are going to discuss curve length or arc length. So, for example, let's say we have a differentiable function f of x, and we want to find the length of the curve from x equals a to x equals b. Now, it almost doesn't matter where a and b are as far as the concept. So I'll just say that this is a here and this is b here, and we want to know what is the length of this curve. In other words, if I take a piece of string or a piece of thread and laid it along here, how long would that piece of string be? Okay. So this is notice here I say this is a justification. It's not a proof. I'm going to use some notation here that isn't actually mathematically rigorous, but the purpose of this video is to give you an overview understanding of this concept. I think math professors would be upset with me if I were to actually use the word proof to describe what I'm doing here. Okay. So the idea and the justification for finding this arc length is to make lots of small right triangles. So, let's see, if I take this and I just draw a straight line here, I know that the dark line that I drew in here must be can be calculated using the Pythagorean theorem. And then, draw another line here. I'm going to use a red marker for this. And draw another line here. And then, we can make a little right triangle right there, and then another one here. And, it doesn't really matter how far apart you make these right triangles. When the curve bends a lot, you want to make more of them, and when it doesn't bend as much, you can make fewer. So, maybe towards the end we can go to some extreme here and, make some right triangles here. Right? So we can make lots of small right triangles, and for example, let's name these points here. Let's say this is x1, y1, and then this is x2, y2 right here. Okay. And this length here, well, we can just use the distance formula for any of these little line segments. So remember that the distance formula is the square root, so I'll write it down here. Is the square root of x1 minus x2 quantity squared plus y1 minus y2 quantity squared. Okay. And then the distance formula gives us the length of one of these little segments. And, in calculus, as we always say, if you want more accuracy, do more work. Make smaller right triangles and make more of them. Okay? So we've seen a lot of these examples before with solids of revolutions, area between curves, that ultimately what we end up doing is we take the sum of an infinite number of line segments, and we take the limit as those line segments go down to 0. Okay? So take the sum of infinitely many line segments, and each segment is infinitesimally small. So this word here, and it's a real word, means that as small as possible without going to 0. Okay? As small as you can possibly go without actually going to 0. Now, and this is the part of the video where we get a little bit loose with the notation here, but this is a justification, not a proof. Sum of infinitely many in calculus will eventually mean taking the integral. Okay. And we've seen these types of example in more detail before with the fundamental theorem, with finding volumes of solids of revolution and volumes of solids with known cross sections. And ultimately, once we work out all the details, we end up taking the integral from a to b. And here's the thing that's important. these, like x1, x2, y1, y2, we can rewrite them as, and I'm going to write it this way over here. I'm going to erase this just so I have a little bit more space to write for the next one. This little length right here is dx, right? Delta x, or the change in x. And then this length up here is dy, or the change in y. And we use dx, dy to represent the parts that get infinitesimally small. So we could use x1 or x2 minus x2 or y1 minus y2, but you know, in calculus we typically use dx and dy as our notation for change in x and change in y. So we take the sum of an infinite number of line segments, and the length of each of these line segments is the distance formula, is the square root of dx, the change in x squared, plus dy, and the change in y squared. And I'll put these in parentheses here, just so that it's clear that it's the dx here is one variable, and dy is another variable. Okay? So really, if we want to find the arc length of this curve, then we have to do this calculation. Now, and this is the fundamental idea behind it, it is really just the distance formula, but calculated for an infinite number of distances, and each distance is really, really small. That's the part that makes this a calculus problem. Okay? Now, we can't actually evaluate anything, or this isn't very useful in its current form, so I'm going to do a little bit of extra work on this in order to make it useful. So the first thing that I'm going to do is factor out dx squared from both of these terms. And at this point, I'm just going to ask you to understand why I'm doing this, and I'm going to ask you to understand how I'm doing this, and at the end of the video, I'll explain as to why I'm doing this. So, as I said, I'm going to take whatever's in the square root here and factor dx squared out of both of them. Okay. Let me just rewrite this a little bit cleaner here. So I'm going to factor dx squared out of both of these terms. Well, once I take out dx squared out of here, now all I have left is 1. I shouldn't even have a square there. All I have left now is 1 in here. Okay. And then what I have in here, and I think I should write it this way, it'll be a little bit better. Don't know why I did that. Once I take a dx squared out of here, what we end up with is dy squared over dx squared. Dy squared over dx squared, because pulling a dx squared out of there. Okay. And now from here we can do some simplifying, and you'll see that this becomes something that looks kind of familiar and useful. So now still the integral from a to b, the square root of 1 plus, now this dx squared and the square root, I could pull it out and it just becomes dx. And then here, dy squared over dx squared, we can regroup it in this way, dy over dx squared. And so hopefully now things look a little bit more familiar. This is the integral from a to b of the square root of 1 plus dy dx quantity squared. Okay, so all of that is in the square root, and then there's a dx out here. And if you notice, dy dx right here, that's just the derivative. That's the derivative with respect to x. So we want to find the arc length right here. The formula that we can use is the square root, or the integral from a to b of the square root of 1 plus f prime quantity squared dx, or we could use dy dx quantity squared. So this is taking the derivative and then squaring it, fitting it inside the square root here, and then evaluating the integral. So the two ways that we write it here, these are the formulas for finding arc length given any particular continuous and differentiable function. Now I want to point out a few things. Again, there was just some like symbol pushing around here. I'm just working out some algebra skills and tricks here. Again, it's not really a proof. If I really did a proof, it'd be much longer and there'd be a lot more details. But hopefully you get kind of the intuition, the idea behind what we're doing here. Alright, so I'm going to end this video here, and then we'll look at the next video where I show you how to use these formulas.